If you feed a universal Turing machine a while loop, you run into an immediate physical problem. You cannot know if the machine will eventually halt and produce an answer, or if it will keep spinning forever. Any formal programming language capable of describing every possible terminating computation is mathematically forced to allow non-terminating ones. Because of this, there is no effective method to calculate a strict upper bound for a program's execution time simply by inspecting its structural code. You have to run the code to find out, and it might run infinitely. To establish a provable mathematical relationship between the physical structure of a program and the time it takes to execute, we have to intentionally abandon Turing completeness. True predictability cannot be layered onto a general-purpose language. It requires building a specialized syntax from the ground up, designed so that infinite computation is structurally impossible. This is Dennis Ritchie's draft dissertation, titled Program Structure and Computational Complexity. To achieve strict predictability, Ritchie made a specific engineering trade-off. He completely removed standard conditional branching and unbounded loops. He replaced them with a highly restricted architecture known as a loop program. In this new system, all iteration limits are strictly and physically enforced before the execution of the loop even begins. By deliberately crippling the language's capabilities, Ritchie turned the existence of a computation bound from an unprovable postulate into a provable theorem. Ritchie's theoretical machine begins with a baseline hardware model. It contains an unlimited number of registers, with each register capable of storing unbounded non-negative integers. This document defines the entirety of Ritchie's permitted syntax. The machine operates on exactly 5 instructions. The first 3 instructions, setting a register to 0, incrementing it by 1, and copying values between registers, are the only permitted methods for altering data. The 4th instruction is the loop. Its mechanical constraint is absolute. The iteration count is permanently locked based on the register's exact value at the exact moment the loop is encountered. We can see these instructions combine to perform basic arithmetic in example 1.2 from the text, which details the brief sequence required to double the contents of register X. Because you cannot alter the loop's iteration count from inside the loop itself, this locked-at-entry mechanism structurally guarantees termination. An infinite loop is physically impossible within this architecture. To measure the complexity of this architecture, Ritchie assigns a mathematical ordinal, represented by the Greek letter alpha, to every loop program. The baseline measurement is straightforward. A program containing absolutely no loops is assigned an ordinal of alpha equals 0. Instructions written as loop n, where n is greater than 1, conceptually expand into dynamically nested sequences of basic loop 1 blocks. The assigned ordinal alpha scales directly in tandem with this depth of nesting. As the ordinals increase, they map to exponentially deeper layers of syntactical logic within the program. Ritchie successfully took a visual property of code, its physical indentation and nesting, and turned it into a strict mathematical metric for measuring computational capacity. This architecture leads to Ritchie's core result, the bounding theorem. It proves that any loop program's execution steps are strictly bounded by a specific function, denoted as f alpha of x. This page outlines the formal definition of that bounding function, beginning with the finite base cases for an ordinal of 0. Moving to successor ordinals, the function handles iteration by taking the previous level's function and composing it with itself. Mechanically, this is recursive composition. The output of one functional calculation becomes the direct input for the next, repeating x times. The jump to limit ordinals requires diagonalization over a sequence of functions, shown in the equation at the top. These functions exhibit rapidly accelerating growth. They escalate from simple linear bounds to exponential outputs, visualized here by a stacking power tower. This explosive mathematical growth precisely mirrors the compounding physical iterations demanded by nested loop structures. To categorize these algorithms securely, Ritchie utilizes a property known as computation-time closure. Closure operates with a strict entry requirement, and arbitrary function f is only admitted to the set if its Turing machine computation time is strictly bounded by a function b that already exists within that set. The rule is also reciprocal. If a bounding function exists in the set, the function it bounds is guaranteed to be included as well. This property allows Ritchie to define robust classes of functions, which he labels L alpha, based entirely on their execution bounds. Closure establishes a self-contained theoretical ecosystem. Inside it, the complexity of the code and the absolute limits of its execution time remain permanently linked. Ritchie connects his highly specific loop architecture to the broader landscape of formal language theory. He reveals an exact alignment. For ordinals of alpha greater than or equal to 2, Ritchie's loop classes map perfectly onto established mathematical hierarchies, such as the Grigorski classes and the primitive recursive functions. This alignment confirms Ritchie's programming architecture corresponds precisely to the mathematical structures defined by Grigorski. Abandoning Turing completeness was the precise instrument required to map this relationship. Ritchie proved that the physical layout of syntax, specifically how deeply logic is nested, is a direct, mathematically sound measurement of computational time itself.